We've discussed curves in R3. Now, a curve is a set of points that organize themselves into a certain shape. The example that we talked about was a line. The points on a line can be described by using 3D coordinates and by using vectors. So, for example, if this is some generic point on the line, we already discussed how to use vectors to locate that point. So we would call this vector R, and we needed some point on the line, x0, y0, z0. We used another vector, and the final piece of the story was we needed to know a vector in the direction of the line, called v. Then what we did was describe the points on this line using this vector equation. A line is only one of infinitely many different curves. We would like to describe any curve in R2 or R3. Remember that if we had this vector with components a, b, and c, and if we put this back in to the vector equation that we've got for the line, what we found was that the points on the line had this component form. It was x0 plus at, y0 plus bt, and z0 plus ct. The point of showing this to you is that each one of these components is a function, and that's the key here. We will generalize this to any curve in R3. And we do this using what's called a vector function. So when we talk about vector functions, there is some curve in this three-dimensional space, that kind of thing. We are going to describe a point on that curve, call this the vector R. Now, we are going to have the x being a function. This y component will be some other function, and the z component will also be a function. And it's exactly the same idea as what we did for the line. Each component is a function, but these don't have to be linear. So these are just some sort of general function. Each of these things here that I've written is what's called a scalar function. Scalar functions are the kinds of functions you've seen in Calc 1 and in Calc 2. So when we have a scalar function, I'm going to write it like this: one input and one output. So essentially this rule f takes a real number and it turns it into some other real number. You're taking a point on the number line, you're applying this rule f, and it will produce a new point on the number line. So each of the components inside of our vector function is a scalar function. When we have this vector function, so this is our input, but the output is a vector. So this rule r takes a real number, and then it returns a vector. It returns a point in R3. We are taking some number here, we're applying this rule r, and it's going to produce some new vector. It lives in R3. You've already had some experience with vector functions. This is the basis for parametric curves in Calculus 1 and 2. Parametric curves are discussed in your textbook in chapter 10.1, but I'm going to review them here because they are the basis for everything that we're going to do when we talk about space curves. If we are going to talk about a unit circle in R2, a circle is a geometric object. It's a collection of points that has a certain pattern. Each point on the circle can be talked about with two coordinates, x and y. Now we can describe a unit circle as x squared plus y squared is equal to 1 when we're in Cartesian coordinates. What we want to do is come up with what's called a parameterization. And when we talk about parameterizing the curve, we're trying to find a one variable function to locate points on the curve. We are now going to come up with some function of t that describes the x position and some function of t that describes the y position. One of the things you should have seen in calculus is that you could take cosine of t for the x position, sine of t for the y position. This is sometimes how cosine and sine are defined. They're called circular functions. If you take a look at x squared plus y squared, you'll get cosine of t squared plus sine of t squared, and you know this has to be 1. So these points satisfy the equation of the circle. And that means if I were to take this vector function, cosine of ti plus sine of tj, which we could write in this vector form, this is a parameterization of the unit circle. This will allow me to describe the points on the unit circle in R2 only using one input variable. All I have to do is supply you with a value of t, and then I can tell you where to stand in space. Now note, this tells you more than just points in space. This is the nice thing about parameterization. It also tells you a direction, how you will move across those points in space. So if we talk about the unit circle again, any point is given by cosine of t, sine of t. When t is equal to 0, this is my location. When I'm at time pi over 2, I will now have a location of 0 and 1. So up here is where I need to be located. So what's happened is that you will have a sense of direction to this curve. Not only will I be walking across the right points, it will tell me that I have a counterclockwise direction to go through all of these points. So you can see inherent in a parametric description is a sense of motion. Now note, other parameterizations are possible. So let's say you wanted to move across the circle clockwise. So you could talk about this parameterization, sine of t and cosine of t. You could switch the two letters. You're going to cover exactly the same points in the unit circle, but you're just going to move them with a different direction. So for now, we're going to focus on parametrizing curves in R2. And then we will eventually generalize this to R3. Now, some parameterizations are very simple. If I were to talk about the parabola y equals x squared, this is a set of points in the xy plane. I need to find some single variable functions for x and for y. Now, the easiest way to do this is you could say, look, if this is a function of x, then I'm just going to say x is t, and that simply tells me that y is x squared, which is t squared. So a simple parameterization of this curve is t in the I direction and t squared in the j direction, which we could then just write as t and t squared. Now, this idea works for y is some function of x. When it's written like that, it's very, very simple. So, for example, if somebody told me that x was t cubed and y was t squared, I would like to know what this curve looks like. So we're reversing the problem here. If I wanted to get a t squared, and I'm assuming that this is going to be some function of x, t squared, I could think of it as t cubed, so I'm choosing the x value as some sort of input, and then I would have to raise it to the power of 2/3. So at the end of the day, what I'm finding is that y is x to the power of 2/3. I've seen this type of curve before. It's got a sharp change in tangent line right there, so it has a point of non-differentiability. Other curves are not given in terms of y as a function of x. We've already seen one with the unit circle. Now, an ellipse is another example. If I have this ellipse, x squared over 4 plus y squared is equal to 1, it is not y is some function of x. It's an implicit curve, not an explicit curve. I would like to take the same approach that I did for the circle. I'm going to try to use that Pythagorean identity. Now, to do that, it's very simple. I'm going to let x is equal to 2 cosine of t and y is equal to the sine of t. Because if you take a look at the equation of the ellipse, remember that the number on the bottom of each term should be interpreted as a square. It's the length of that axis squared. If I were to go x squared over 4 plus y squared, I would have 2 cosine of t squared over 4 plus sine of t squared. That's going to give me 4 cos squared t over 4, sine squared t over 4. The 4's will cancel out. I'll have a cos squared of t plus a sine squared of t, and I know that that equals 1. And that satisfies the equation of the ellipse. So that means then a parameterization of this ellipse is 2 cos t and sine t. Now, generally, when I have an ellipse, x squared over a squared, y squared over b squared is equal to 1, this parameterization will work. A cosine of t, y is equal to b sine of t. This will always generate the parameterization I need. We want to try to generalize these parameterizations to R3. Now, as an example, we've already talked about a unit circle in R2. So now if I'm in R3 and I give you cosine of t, sine of t, and 1, what curve does this describe? Well, I know if I were to take the x component and the y component squared, I'll get cos squared t plus sine squared t, and that equals 1. So this satisfies points on the unit circle. What about the z? The parameterization that I've stated here will satisfy points on the unit circle in the z equals 1 plane. So if I now talk about a three-dimensional coordinate system, and it looks something like this with an x and a y, I have now successfully described points that live on this unit circle with a 1. I need a little more information to be able to properly describe points in R3. Now, I can also extend this further. So, for example, if I continue to use cosine of t and sine of t for the x and the y, what change does this make? So we still have x squared plus y squared is equal to 1. This is a cylinder in R3 because it's missing the z variable. So that means it would extend in the z direction. So points given by this r of t are located on a curve on a unit cylinder. And I'm going to try to show that to you with some pictures. I'm going to draw the surface of this cylinder like so. And remember that the cylinder extends forever and ever in the z direction. It has these two coordinates like that. If I were to take a point given by that parameterization, so for example, when time is 0, this is going to tell me that the location that I'm interested in is 1, 0, and 0. So this is going to put me at some point here. As t increases, the z value increases as well. And it increases linearly. So it goes up an equal amount as we go forward. As I continue to go forward in this t variable, I wrap around this cylinder. And it continues to wrap around. And it wrapped around the cylinder from before, from negative times. And what happens is it generates a certain kind of curve called a helix. Now, a helix isn't just some mathematical object. This is actually found in nature. This is actually the shape of the strands in DNA, and it's also the path of a charged particle in an electric and magnetic field. So it's kind of amazing that such a simple curve can describe things that happen in real life. Another useful application of this idea is the intersection of surfaces. Now, when surfaces intersect, they will generate some sort of curve. What curve? So, for example, the surface described by this is an elliptic paraboloid. So it's a bowl shape. Y is equal to x squared. Well, this is a parabolic cylinder. I would like to know how these things intersect. A parabolic cylinder kind of looks like the curve y equals x squared, except it extends in the z direction in three-dimensional coordinates. And the elliptic paraboloid is essentially a bowl shape. Now, you can see from my picture, these things touch in some curve. What is its parameterization? Well, it must satisfy the equation of both surfaces because it lives on both surfaces. And as a result, if x is equal to t, y can then be x squared, which is t squared from the parabolic cylinder. And then we're going to sub this into the other equation. That means z has to be x squared over 4 plus y squared, which is going to be t squared over 4 plus t squared squared, which means z is t squared over 4 plus t to the power of 4. And that means then a parametrization for the curve of intersection is t squared over 4 plus t to the 4. Now, the best way to visualize space curves is with graphing software. Drawing them by hand can only take you so far, but the best way to do it is to learn with some graphing software. There are so many options out there. Simple search on the internet will allow you to come up with visualization tools far beyond what you can do by hand.